Hi guys, welcome to our fourth video in chapter two. And this video is going to talk all about errors, right? So I got errors all over the place here in my memes and stuff. And errors are good, but I want us to specifically focus on if we are in a science class, what is considered an acceptable error to give, an error source to give, and then how do we calculate percent error once we know a given piece of information. So I want to start by breaking down our types of error in general. Okay, so we have three types of error. First type on my left here is called blunders. Okay, so these would be errors caused by carelessness. This would be something like I spilled a liquid, so we couldn't measure it. I measured it wrong. I used the wrong tool. I grabbed the wrong chemical. These are your classic like mistakes that you make in lab. This is a mistake. And the key is that you should know is that this can be redone and fixed. Okay, so a blunder is something that you say, okay, I measured the wrong liquid, so we have the wrong volume. I would say, okay, go ahead and redo it. That's how you know you have a blunder. These are actually we want to avoid giving blunders as sources of error because the thought is if we could go back and fix it, then we should go back and fix it. Okay. So I'm going to focus more on systematic and then random errors. Okay. So systematic errors, just so that we have, just to be specific, this is an error that is identifiable and can be fixed. Can be fixed. Okay. And these tend to cause lopsided data. Sometimes it favors high values, low values, and sometimes it can be in the middle. But the thing about a systematic error is that it is due to our setup. Okay. So this error, I'll write it over here. This error is due to our setup. It is not due to any other aspect, right? It's not random. It's in fact due to how we have this set up. Okay. If I am measuring the time that it takes for my ball to get from A to B, and I start my stopwatch after 5 seconds, that is a systematic error. I have it by part of my setup, I have missed the first 5 seconds of my lab. Okay, so that would be an example, all right? And we can break that down into four aspects. We could have a systematic environmental error. This could be a problem with the surroundings influencing the lab. Maybe we have a really humid classroom one day, and that affects how fast a plate of water evaporates. Okay, so it would slow down our evaporation due to the surroundings, not due to the experiment. We also have observational biases. If I am reading my tools incorrectly, like say I'm not getting down at eye level to read a graduated cylinder and I'm looking down at it, all of my measurements will be off. They will actually be slightly lower than they should be. Okay, if I'm standing instead of sitting when I read my graduated cylinder. We have instrumental bias, and this is a great one. This is a really good one for you to include if you can find it, because this would be where, say, your tool is not calibrated correctly. I'll say calibration. This is where maybe my thermometer is supposed to read 10 degrees Celsius, and in fact, it reads 9. Or if I'm using a stopwatch and instead of starting at 0, my stopwatch starts at 2. Okay, these would be instrumental errors. And then we have theoretical errors. And I am actually not going to go into this too much. This would be where your experiment has a flaw on setup. You worry about that more when you are setting up your own experiments. Okay, so systematic errors are good. Random errors, these are every single scientist, whether it's you, a rookie in the lab, or a professional scientist, every scientist deals with random errors. And the key about random errors is that they are uncontrollable. Okay. And these are caused by random fluctuations in variables. It could even be as simple as like just getting an outlier as a response. Okay. So like you get a sample kind of outside of what you'd expect for data. You've got a random error there. Maybe we just happen to maybe we happen to see like a hot spot in lab where the temperature of the room goes up in one area a little bit, causing our temperature of our experiment to rise. Well, that would affect the rate of reaction and stuff. And this would be an example of, it says here, an environmental random influence is when the environment unpredictably changes and results, which affects the results of the experiment. Okay, so it's again, unpredictably changes. That is the key for our random errors. And then observational, this is when, similar down here, where if we think about systematic, you're reading a tool wrong. You're using a tool wrong for a systematic observational error. But for a random observational error, it's actually your judgment. So when the user's judgment leads to random inaccuracies. So the idea, essentially, maybe if you are wanting to know if Gatorade causes athletes to perform better, maybe you have it in your head already that you think Gatorade is going to cause people to perform better athletically. So your results kind of you pull data that favors that outcome. Okay, so again, another source of error here. Now we do want to avoid that observational error. So when we focus on identifying what are our errors in class, okay, we can focus on observational, environmental, and instrumental for our systematic errors, and we can focus on environmental errors for our random types of error. Okay, so we never really want to say our judgment was the problem because hopefully we can go back and fix that. You guys don't worry about the theoretical aspect. And then finally, blunders would be just redone. Okay, so those are your types of error that you see. Now, I want to go to another topic here. I want to talk about, sorry, let me get rid of this. I want to talk about percent error. Okay, so we know uh, we know that in chemistry, we have what we call tabulated or official values. These can be found in textbooks. This would be something like, for example, the density of water is 0.997 grams per milliliter. Okay. We are going to do a lab where we calculate the density of water. And whenever we take measurements in lab, we know an accepted value of it's always appropriate to give some percent error in our measurements. And in order to do that, we take our percent error, we say it's equal to the absolute value, which means get rid of the negatives, so there's no negatives there, of the measured value minus the accepted value divided by the accepted value, all times 100. So in a quick example, let's say, let me just say example, let's say I measured and calculated the density of water to be 1.10 grams per milliliter. So let's say I did a lab, let's say I did lab 2.1 and I found that to be my answer. Okay. And I'd like to go ahead and calculate my percent error. So I can say my percent error is going to be equal to, well, I can take the absolute value. So that is, I'll just put it in parentheses here. And I'll remember that that's absolute value. It's not as easy to type out here, but I'll say the absolute value of my measured value. The measured value is the value that so let me highlight the measured value here in reddish red here. That's my measured value. And that's the one I got out of lab. Okay, so our measured values come out of lab. So for my percent error here, can I redo it? Okay, fine. I take my measured value, which is 1.10, and I'm going to subtract off my accepted value. Well, now my accepted value is the one that is given in the table, right? The one that we know is well documented, the one from the textbook. That's my accepted value. And in this case, you can see it's a numerator and denominator. Okay. So I'll take my accepted value of 0.99997. Okay. And I divide all that by, let me see if I'll have to draw it. This is not as smooth as a touch screen, but it'll be fine. I divide that by my accepted value again, which was my 0.997. Okay. So again, I've just plugged in here. You can see, maybe I can draw like a line here. You can see my measured value here, my accepted value here, and then my other accepted value here. So you can see where I'm pulling these from, right? My measured value I got from lab, and my accepted value I got from here. So now that I've got lines everywhere, just pointing out where everything came from. Let me just get rid of some of that. A little too much, but anyway, so if I actually got rid of all my numbers, I want to keep the numbers. Let me just delete the lines. Cool, lines gone. And now I'm going to not forget my end part here. I have to multiply by 100. So if I do my math out, I find that my percent error should be Sorry, I knew I did something wrong here. Anyway, so I do my math out, and I'm going to get 10% error. And I see that my measured and my accepted values both have 3 sig figs. So I'm going to add my first decimal place to that to give myself 3 sig figs. So the answer would be 10.3. And this is a percentage question. So it's 10.3% as my final answer here. The percent error on this is 10.3%. Okay. All right, we will do more of these in class, and please, of course, ask questions if you have any. Thank you guys for listening, and I'll see you in the next video.